If solar panels are the heart of a PV system, then the inverter is its brain, converting the sun's energy into usable power and ensuring everything runs in harmony. In this module, we'll explore why the inverter is vital to system efficiency, reliability, and performance. The function of an inverter is to convert direct current DC electricity produced by solar panels into alternating current AC, which is suitable for use in homes, industries, and for grid export. The inverter also synchronizes the power output with grid parameters to ensure stable and safe operation. The basic function of the inverter is to convert DC power from solar panels into AC power for your home and grid, while also managing energy flow between the panels, batteries, and the load. When connected initially, the power generated in the PV modules, corresponding to their wattage, travels to the maximum power point tracking MPPT device in the inverter in direct current DC mode at the rated panel string voltage, VMP, maximum power voltage. The most important function of MPPT is to maximize the electrical power output from a solar photovoltaic PV system. The output DC power from the MPPT at system voltage is then fed to inverter to convert the DC power to AC power for catering to load. The surplus DC power at system voltage from the MPPT is fed to Battery Energy Storage System, BESS, depending upon the real-time situation in case of a hybrid inverter, which also has a Battery Energy Storage System, BESS, in the loop. Broadly, the inverter has the following major functions in a solar power system: stabilization of high-voltage DC from the panels to regulated DC at system voltage. DC to AC conversion converts stabilized system DC voltage into stable AC voltage. Maximum power point tracking, MPPT, extracts maximum possible power from PV modules. Grid synchronization matches frequency and voltage with utility grid for smooth power injection. Off-grid inverters, used in standalone systems without grid connection, depend on batteries for energy storage. Often integrate solar charge controllers forming power conditioning units, PCUs, modes, standalone grid-assisted in grid charging. These are much smarter than the off-grid ones because they must synchronize with the grid in addition to the other normal functions of off-grid inverters. Important features of on-grid inverters include providing priority to solar while injecting into the grid, controlling harmonics and maintaining grid stability, operating maximum power point tracking, MPPT, to maximize use of available solar energy, and providing anti-islanding protection. As already mentioned, the on-grid inverter can synchronize with a diesel generator supply as well as utility grid. Common for residential/commercial setups. Directly feed AC to grid with real-time synchronization. Feature MPPT, anti-islanding, harmonic control, and remote monitoring. Efficiency typically greater than 97% with automatic restart when grid returns. Combine grid-tied and off-grid features. Can operate with solar panels, batteries, and grid simultaneously. Intelligent energy management for optimized self-consumption and backup. Transformerless is compact and efficient. Use electronic step-up converters. Isolated include galvanic transformers for separation common in MW scale plants. Based on their architecture and capacity, micro-inverters, one per module, enable module-level monitoring. String inverters. Connect several strings of panels with MPPTs ideal for rooftops. Central inverters, used in utility-scale projects, handle high voltage and current inputs as in large power plants. Maximum efficiency up to 98.6% for top-tier models. European efficiency reflects realistic operating conditions, approximately 98.3%. Temperature derating. Output power reduces beyond 45 degrees Celsius. Cooling methods. Forced air, natural convection, or liquid cooling. Example, SG30CX, 30 kVA output, 3 MPPTs, 200 to 1000 volts MPPT range, IP66 protection. Inverter safety is paramount to ensure user and grid protection. Major standards include IEC 62109 Power Converter Safety, IEC 61727 Grid Interconnection, ASNZS 4777.2, 2020 Australian Grid Compliance, IEC 610006 3- Electromagnetic Compatibility, Key Safety Functions, Anti-Islanding Protection, Surge Protection, DCAC Type 2 SPDs, Overvoltage, Short Circuit, and Leakage Current Detection, Ground Fault, and Grid Monitoring Systems. When choosing an inverter, evaluate AC peak power output required in the grid along with type of load. The inductive load with induction motors, etc., has to be carefully considered while determining the inverter capacity, keeping in view the requirement of full load ampere, FLA of the motors, corresponding to the starting torque. Grid frequency, MPPT capacity to be determined based on the PV array size and configuration and the charging current required for the BESS. MPPT capacity to be suitable for the PVAC output power and grid frequency range. Efficiency, cooling type, and IP rating. Communication and monitoring features. Power generation string-wise is vital and needs to be monitored. Also, the input and output currents to and from the BESS also need to be remotely monitored for better control towards minimizing the losses and fault identification. Ambient temperature conditions, compliance with regional grid codes. Inverter must have the provision of isolation transformer as an inbuilt protection device so that the output to the grid is through the isolation transformer. Match PV string voltage/current with inverter input ratings. Use multiple MPPTs for arrays facing different orientations for maximizing the efficiency of the whole system. Integrate monitoring via RS485/Wi-Fi Ethernet. Optimize string length for maximum efficiency per voltage curve. Isolate AC/DC sides before maintenance. Use lockout/tagout and PPE protocols. Maintain ventilation and clearances. Follow local electrical codes and fire safety standards. Utility Scale Solar Power Plants IFC Guide. Handbook for Rooftop Solar Development in Asia, ADB. Best Practices for O and AMP-M of PV and Energy Storage Systems, NREL, IEC, and BIS standards for PV inverters. Inverters are not just converters. They are intelligent control units, ensuring maximum energy harvest from solar panels and grid stability. Thanks for going through and reading. Don't forget to like, share, and subscribe for more solar insights from I-SED Academy. Please go to I-SED Academy platform for detailed learning about solar technologies.